Hi, everyone. Welcome to our today's webinar. My name is Elvira Redadieva. I'm a product and offering specialist at Leosphere, a Vaisala company. And I'm joining you today from our headquarters in Saclay, France. And it's very nice to see so many of you join us today. So today we will be talking about the Nacelle-Mounted Lidar for power performance testing, as well as the upcoming IC 50-3 standard and the changing power performance testing practice. I will be starting this conversation by providing an overview of the PPT practices in different parts of the world. I will talk about the track record of Leosphere in developing nacelle-mounted lidars, and then we will have Luke Simons from DNV talking about the WindCube Nacelle classification and the IC standards, IC standard in more details. And then Alex James from GE covering the WindCube Nacelle operations, including turbine interface and the installation guidelines. And finally, Hong Lu with NG North America will discuss nacelle-mounted lidar applications such as power performance testing, nacelle transfer function, and yaw misalignment, which the results of this will be based on one of the pilot projects. To present a bit our today's speakers, so on my side, I've been with Leosphere a bit over a year now as part of our product marketing team, and I'm heavily involved in all of our onshore and offshore marketing activities for wind lidar. Luke Simons has been focused on power performance testing of wind turbines for 15 years. As a principal specialist at DNV, he's also an active member of several IC committees, including the 50-3 LiDAR project team. Luke has led research and innovation projects around the application of nacelle lidar, including in complex terrain since 2013. Currently, he's working on a variety of lidar measurement applications to provide the industry with the highest quality results for understanding and managing their assets. Then we will have Alex James, who holds a master's degree in mechanical engineering from Cornell University and has worked in the industry for over 6 years now. 5 of those years have been with GE onshore wind, improving performance through modeling and measurement. He has been a user of ground-based lidar data for performance measurement throughout that time, and more recently taking on additional responsibility for nacelle lidar turbine integration for the GE megawatt constraint fleet. And finally, Hong Lu with NG North America. Hong has a PhD in atmospheric science and has over 20 years experience in the renewables industry, supporting project development and operations in North America. Hong currently leads the resource assessment team and manages power performance measurements for grid-scale renewables at NG North America. And a few housekeeping tips before we go into more details with our presentations. There is a Q&A button that you can use to ask your questions, and we will try to answer as many of these questions as possible during this webinar. And if we don't get back to all of your questions, we'll try to connect with you after the webinar. We also have a resource section at this platform where you can access all the additional information shared by our speakers on the WindCube Nacelle and on the power performance testing in general. Also, if you have any technical problems, you can click on the help icon to find answers to the most common technical issues. And well, this webinar is recorded as always, and we will communicate the link to the recording in a few days after this webinar. All right, and here we have a small poll to understand a bit better our audience. We would like to know if you are performing power performance testing campaigns currently, if it's onshore or offshore, or if you are not yet involved in this kind of applications. So I'll give you just a few seconds to reply, and we can move forward to see your answers. All right, so as you can see, the majority is performing PPT onshore, and almost half of the audience don't. So I think it's going to be interesting for you to learn more about this, about the practices for power performance testing. All right, so let's dive into our topics today. So on my side, I will start this discussion by doing a small overview of the wind energy trends and how they affect the power performance testing practices. I will show you some of the interview takeaways on the PPT practices in different parts of the world, and then walk you through the history of Nacelle-Mounted Lidar at Leosphere, and some of the projects that we've been involved in, and how those have paved the way for the upcoming IC standard and the WindCube Nacelle classification. So there are some interesting trends today in the industry, such as, for example, the continuous growth of wind energy additions, both onshore and offshore. We see that the mature markets continue to invest in wind energy, but there is also interest in emerging markets. And we also see that wind farms are increasingly built in quite hard to access remote areas. So offshore, these are deep water installations far away from the shore, from the ports. And onshore, these are wind farms that are built in complex terrain. And as you may know, also the wind turbines are continuing to getting taller, more powerful. Already today, we see turbine manufacturers adding 14, 16 megawatt turbines for offshore applications. And of course, all of these trends affect the power performance practices as well. It's getting more and more important to get the most out of your wind farms, to get the strongest performance and economic value. And this is where the limitation of met mass and traditional measurement systems are visible. Met mass are becoming more challenging to install, more expensive, and especially now we see the additional value that Nacelle-Mounted Lidar brings, thanks to its accuracy, flexibility, and cost efficiency. In this slide, I would like to present you some of the takeaways of the industry surveys and interviews that we did with key wind developers, opinion leaders, and turbine manufacturers in different parts of the world. We were trying to compare the different measurement instruments used for power performance testing, the frequency of this kind of campaigns, and also the number of turbines that are tested. And the practices are quite different in different parts of the world, but what we see is that the use of LiDAR is growing, especially in key markets, and there is interest for nacelle-mounted lidar for power performance testing. And we expect this trend to continue. We expect the power performance campaigns to increase thanks to the installed capacity growth, but also this additional cost pressure to get the most out of this newly built wind turbines. There is a positive trend for nacelle lidar over MetMast, also thanks to the upcoming IEC standard and the price competitiveness of nacelle-mounted lidar compared to a MetMast, but also this track record of the industry, both in technical and commercial projects over the past 10 years. At Leosphere, we have quite a long history of developing nacelle-mounted lidar. We started back in 2011 with a two-beam model that was improved in 2015, adding 3D capabilities and becoming a four-beam lidar. And today, with WindCube Nacelle, we're able to meet industry needs both onshore and offshore, both for smaller and more bigger turbines. And this product development is fitting within the important industry milestones. So here there are two notable projects to talk about. First one is the EUDP project with DTU, Siemens, and Ørsted, where the two-beam lidars, nacelle lidars, were used to define calibration and power curve measurement procedures. And during this campaign, it was demonstrated that using nacelle-mounted lidar instead of MetMast or other traditional measurement systems brings significant cost savings, especially for offshore applications. Another project to highlight here is the DTU UNIT project, where a new generation of nacelle-mounted lidar was used. The main objective of the project was to develop new validated procedures for wind turbine power curve measurements and load assessment that can be universally applied. And the project has demonstrated that the same or superior level of accuracy can be achieved with nacelle-mounted lidar. And ultimately, the project was aimed at forming sound scientific basis for the next generation of international standards. So these two projects paved the way for the current IEC 50-3 standard, and over the past years, Leosphere has actively participated in the preparation and definition of the standard, bringing its expertise to the IC working group. And another milestone here is these key pilot projects that we performed with various industry leaders in different parts of the world to demonstrate the suitability of the nacelle-mounted lidar for power performance testing. And today we see that the industry is ready to perform commercial campaigns with nacelle-mounted lidar. And as a conclusion to my presentation, it's fair to say that the industry is ready. The standard is on its way and it further enhances this confidence in the nacelle-mounted lidar and provides clear guidelines for PPT campaigns in onshore flat terrain and offshore. And in line with this upcoming standard, we are also finalizing the WindCube Nacelle classification. Although already today, it is a ready-to-go solution for PPT campaigns and other type of applications, thanks to the adoption by the industry through various pilot and commercial projects in different parts of the world. So this will be the end of my presentation. I will now turn over to Luke Simons from DNV. Thank you.
All right. Thank you for the introduction. Thanks to the listeners today, and also thanks to Vaisala for having DNV participate in the webinar. Moving right along, we'll take a quick look at my short agenda. We're going to do a bit of an overview to the Nacelle LiDAR standard and how it fits in the IEC framework. Then we'll skip directly to the classification uncertainty method defined within the new standard and take a brief look at some ongoing measurements. If we consider the overview here, so currently the IEC 61400-12, the power performance standard, is undergoing a restructuring process. If we look at the new structure, the main thing to be aware of here is that the wind measurement methods are being treated separately from the power performance guideline. So there will be one standard for instruments mounted on a mast, one standard for ground lidars, one standard for nacelle lidars where we're focused today, and then another standard here in the bottom left of the framework for the floating lidar measurements. So this restructure should, in theory, allow for easier maintenance of the individual standards. We've seen this play out a bit already with the nacelle lidar standard being developed in about 4 years, whereas the previous, most recent edition of 12-1 took at least twice that long. So let's review a few key definitions and acronyms. We'll be talking a lot about intermediate values. These are the direct measurements by the LiDAR that are input to the wind field reconstruction to achieve the final values. An example is a line of sight wind speed, which is the direct measured value of the LiDAR. We'll also be using the acronym EV, not to be confused with electric vehicles. But in this context, we're referring to environmental variables such as air temperature, turbulence intensity. The next acronym is WFR, or wind field reconstruction. This is the algorithm where the intermediate values are input to the model, and then the output values are the final values such as horizontal wind speed or wind direction, represented here on the right. So the ability to carefully calibrate the intermediate values, this is one of the primary differences between the nacelle lidar methods we're going to explore versus the ground lidar approach that we've also been using over the last several years. So now that we've introduced the main concepts, we can move into the uncertainty assessment. And for this, the question is, why do we classify a lidar? And as I've already mentioned, we can calibrate those intermediate values. And during this process, the results are going to be subject to a specific set of conditions that will impact the quality of the relationship and thus the uncertainty of the calibration. After the calibration, the LiDAR is installed on a test turbine for the final campaign. And during the campaign, the LiDAR might be subject to completely different or maybe slightly overlapping conditions than what occurred during the calibration. So the additional range of conditions introduces more uncertainty in the measurement, and the classification allows us to estimate any uncertainty specific to those conditions. So in order to do that, the standard gives us guidance to assess the sensitivity on the measurement accuracy. The sensitivity is assessed using a two-step approach, both utilizing the intermediate values and then the final values. And if we look a little bit closer at that first step, there's a minimum list of EVs that are going to be considered in the sensitivity analysis, which we've listed here including things like air temperature, cloud height, aerosol density, turbulence intensity, to name a few. And in order to assess the sensitivities, we're allowed several methods, including comparison to reference systems, such as what we would do in a field test, lab testing, and even simulation. So for each of these EVs, the data are typically presented similar to the plot on the right, where the y-axis is the error in wind speed between the LiDAR and the reference measurement, and the x-axis is the EV range being considered. So this is just an example ground LiDAR sensitivity showing how the wind speed bias or the error could change as the wind shear changes. So based on these relationships, we can determine if there is sensitivity and then what parameters to use to calculate the related uncertainty. So next we have some general criteria for the sensitivity test, stating things like the field test site must meet the terrain requirements of a calibration site for Nacelle LiDAR, which is a bit more strict than what we're used to with 12-1. Some general recommendations to measure as wide a range of EV conditions as possible to allow as much transferability to the final test sites as we can. And then the last bullet on the top part here is to say that some decorrelation methods may be needed to better assess the sensitivities. For instance, if air temperature and air density are both considered significant, it's likely that some decorrelation is needed to determine which is really the primary EV and to ensure we're not double counting the uncertainties. In the lower part here, if we look at a simplified version of how to apply the sensitivity test results, in order to calculate the uncertainty during a field campaign, we can see the uncertainty of the calibration already captures some of the sensitivities, and it's necessary to determine what additional conditions now need to be considered. Once we know the range of additional conditions, we can apply that range by the slope of the relationship from the sensitivity test. And then we combine the values in root sum square for the different EVs to come up with an overall sensitivity. Something to keep in mind, if the conditions during the power curve test are the same or they're within the range seen during the calibration, no additional uncertainty for these is going to be required. And additionally, if the uncertainty contribution is less than half of the calibration uncertainty, we can also consider it to be negligible. So if we consider step 2, which is the evidence base, the evidence base that's used to confirm that the wind field reconstruction model is not sensitive to any EVs. For each of the campaigns in the evidence base, there must be a reference measurement, such as a met mast, to compare with the Nacelle LiDAR measurements. And the evidence base requires at least 5 campaigns, where a minimum of 2 of the campaigns, the LiDAR must be installed in an operating turbine. These are the on-nacelle tests. And then at least 3 of the campaigns, the Nacelle LiDAR is installed on a platform or directly on the ground. So why do we have to consider these 2 scenarios? The off-nacelle test tells us if the wind field reconstruction really works and can provide accurate final values in a stable environment. The on-nacelle campaigns are the ultimate test of whether the wind field reconstruction can provide good final values while tilting, yawing, being blocked by the blades, and all the other issues associated with sitting on top of an operating turbine. The criteria that must be met to satisfy the evidence base varies between these 2 tests. The off-nacelle test requires a single parameter regression of the horizontal wind speeds to have an arc squared greater than 0.97 and a slope within 2% of unity. And the on-nacelle test requires that the mean bin-wise deviations between the Nacelle LiDAR wind speed and the reference wind speed are within the uncertainties of the reference measurement. Another thing to keep in mind is that the applicability of the evidence base does have some limitations. For instance, we're not going to use tests from a 50-meter hub height, 50-meter rotor diameter turbine and assume it's suitable for a 150-meter hub height, 200-meter rotor diameter turbine. There's simply too much potential for changes in the sensitivities. So we have a few rules which I've shown in red here when you're comparing a power curve campaign to the campaigns in the evidence base. First, one of the rotor diameters in the evidence base needs to be within 30% of your test turbine rotor diameter. Next, one of the measurement ranges in the evidence base needs to be within half a rotor diameter of the planned measurement range for your test turbine. And lastly, one of the hub heights in the evidence base needs to be within 30% of the hub height of your test turbine. Again, this is all well defined in the standard. But if we move on to actually look at some data, this is going to be part of the final evidence base. On the left is the off-nacelle result comparing data while the LiDAR is fixed on a platform, comparing the data to a reference mast located in between the beams of the LiDAR swept area. We can see that the criteria are easily satisfied since the R squared is greater than 0.99, where 0.97 is the minimum, and the slope of 1.001 is well within the 0.98 to 1.02 limits. The plot on the right is data from a completely separate on-nacelle turbine measurement campaign. This plot shows the bin-wise mean deviations between the nacelle LiDAR and the reference measurements. The standard says that the deviations must be within the uncertainty of the reference device. That's represented by the blue dots. We see that the criteria are satisfied within the majority of wind speed bins, but we do have some divergence at low winds near the turbine cut-in and also at some higher wind speeds. For the low wind deviations, it has triggered some additional investigations, which we've only just started, so I can't go much further with that today. But moving on, the outcome of the classifications that will know the sensitivity to a list of significant environmental variables, and we expect to have an evidence base that shows the wind field reconstruction is not sensitive to the EVs and that no additional uncertainty should be applied related to the wind field reconstruction. It will then be up to the end user to determine what additional uncertainty is needed to adjust for differences in the EVs between the calibration and the final measurement campaign. So in summary, we've reviewed the two-step approach for nacelle LiDAR classification to consider how the measurement system and the algorithm are sensitive to changes in environmental conditions. And while we only had a glimpse of the data, the final results of the WindCube Nacelle LiDAR classification are underway, with delivery expected prior to publication of the IEC standard, allowing industry to hit the ground running using the WindCube Nacelle for both onshore or offshore power curve testing. So that's it for me, and I will pass it on to Alex and look forward to the questions.
Thank you, Luke, and thanks for that overview. Thanks to Leosphere for including GE in this webinar for everybody today. We at GE are pretty excited about the value that nacelle LiDAR can potentially bring to power performance testing, and to that end, we currently have 5 evaluation campaigns underway that we're actively monitoring and actively analyzing the data from. And again, we're pretty excited about what the nacelle LiDAR technology is going to do in our future for power performance testing and also for wind field measurements. So prior to getting to the 5 campaigns that we currently have, we needed to get the devices installed in the turbine. So today I've got a couple practical points to talk through on things to keep in mind when planning a nacelle LiDAR campaign. And so with that, I'll jump right in. Got a list of items here. You could think of it somewhat as a checklist. There may be some other odds and ends that certainly need consideration, but these are the main points that are really important when thinking about integrating a nacelle LiDAR with your turbines. So first and foremost here is safety. We want to make sure the nacelle LiDAR stays on the turbine for the intended period of time. That sounds kind of dire, but it definitely it's important, right? Safety is number one. So 2 points there specifically are access to an anchor point and a lightning ground. So working through with the turbine OEM to determine appropriate points for those two. Loading is the next one here. Obviously, we want to make sure that the turbine, the nacelle shell, can handle the extra loading that will be placed on it. There is certainly a wind drag on the nacelle lidar devices, and that can introduce higher fatigue and extreme loads that need to be evaluated. Next here is location. This one's pretty critical for a number of reasons. First off, are there any downwind items such as a nacelle anemometer or some sort of cooling device for the turbine that could be obstructed by the nacelle lidar device? And then equally as important for your measurement for sure, will the beams clear the nose cone? So the lidar beams need to have line of sight out into the wind field in front of the turbine, and if there's not clearance over that nose cone, there will be some impact to the data quality. Next on the list is how will the data be retrieved? So typical for a MPPT, a power performance campaign, there can be a dedicated data collection system that works via radio and cell modem. It's also possible to integrate data into turbine SCADA systems, though that path is typically much more complex and has its own roadblocks in terms of cybersecurity. Next on the list here is power. So obviously our nacelle lidar devices need power to operate. So do they have access to grid power from the turbine? If not, do you need a standalone power system for your measurement campaign? Next on the list is a processor. So typically nacelle lidar devices have some sort of computing processor that takes in the sensor, the laser data, and processes and computes the wind field. So that's a separate unit typically. Where do you mount that? Usually inside the nacelle, I would say. Keep it out of the elements if you can. But inside the nacelle, you need to scope out a spot that's out of the way, right? You don't want tripping hazards for technicians. It also needs to be mounted in a secure location that is not going to subject the processor to too much vibration. So it's important to keep that in mind as well. And lastly, here I've got environmental sensors. Do we have dedicated devices on the nacelle lidar device? If not, do we need to install them? Depends on your purpose, depends on the scope and the target of your campaign. And just something to keep in mind there, because it could be some additional installation steps needed for environmental sensors. So the key takeaway here is for a nacelle lidar campaign, engage early. There are answers to all of those questions that we have in hand now for all the GE turbines for sure. But every installation is unique, and they may need adjustment to the standard procedures, the standard guidance based on site-specific conditions, based on the objectives of the campaign. So again, engage early, make sure that there's enough time to answer all these questions fully, and make sure that we keep the lines of communication open to ensure a successful campaign. My last slide here, I've got some examples of what we've done for some of our campaigns, just to illustrate some of the points. In the upper left here, I'm showing a diagram of the WindCube Nacelle interface, the tripod foot mounting interface. In green here is the laminate of the nacelle shell. And we've actually incorporated a custom plate here in blue that is fabricated from steel that increases the joint strength. It's really the height that we're looking at there that is important. So we're adding some height to that joint. to make sure that the torquing force of that clamped joint doesn't damage the nacelle shell. So again, engage early. Those custom plates need to be fabricated and installed ahead of time. Need to be fabricated ahead of time so that they can be installed on time with your campaign timeline. Over to the right here is an example of an anchor point. So for GE turbines, we typically specify the nacelle lifting hooks as a good anchor point. They're rated to lift the nacelle, so they have the strength required to safely attach a nacelle lidar device. One key point here is to never use personnel tie-offs for safety anchor points. Those personnel tie-offs are for personnel only, and using them for a nacelle lidar jeopardizes their viability for their intended purpose and could have obvious safety ramifications in the event of an emergency. Moving down to the lower left here, there's many features on a nacelle. It could be structural ribs, it could be openings, it could be safety rails, it could be other hardware that's installed, such as a nacelle anemometer. And the diagram I'm showing here is, it sort of illustrates how we need to thread the needle a bit on the location of the device. It can be quite limited to find a spot that's suitable on a turbine nacelle. So certainly work with the turbine OEMs to find those locations, and it can be somewhat restricting on where you place the device. So again, engage early, make sure that you have a location identified, because it's not typically as simple as just pointing to a spot on the nacelle and start drilling some holes. And then lastly here on the lower right, getting back to the beam clearance point on the first slide, the fore aft location and the height of the nacelle lidar device can influence that beam clearance. So again, finding that location where you can be free of nacelle features and you have room to lay out the tripod and drill the holes, very important there. But also, as I just mentioned, height equally as important. Typically the nacelle lidar devices have adjustable height, and that's certainly helpful. But when planning the installation location, it's important to make sure that you have the right combination of fore aft location and height to ensure that beam clearance. So with that, thank you all for listening, and happy to take questions, or I have my email on the front slide. You're welcome to email me with any questions about nacelle lidar installation. And with that, I'll hand it over to Hong Lu from NG. Thank you.
Thanks, Alex. Good morning and good afternoon, everyone. Thanks to the Leosphere for inviting NG to this webinar. I'm going to present some results from a joint study that we carried out in partnership with GE, Leosphere, and the DNV. But first, I would like to acknowledge my co-authors listed here, including my colleagues at NG and those from our joint study partners. So going to the objectives of the study, and this joint study was to support our power performance testing program in anticipation of the new IEC standard -50-3 using Nacelle-Mounted Lidar, which Luke has described previously. As an owner and the operator of the wind projects, we would like to optimize our power performance testing program by evaluating how the different IEC standards and technologies affect the power performance testing results, and how the wind measurement locations could impact the testing results. With the evolving power purchasing agreement vehicles in the market, nacelle transfer functions become important to accurately calculate the proxy generations. We would like to validate the nacelle transfer function used by the wind turbine OEMs. Yaw misalignment is another important aspect that we would like to verify in our operations. For this study, we deployed a 4-beam WindCube Nacelle lidar. An IEC-compliant hub-height permanent mid tower and a WindCube ground-based lidar, which is located here. And this is actually our testing turbine. In two-dimensional view, as you can see it here, the permanent mid tower PMM and the WindCube ground lidar are about 2.2 rotor diameters upwind of the testing turbine. Two blue lines, green lines, represent the IEC valid sector. The prevailing wind direction is from south. The chart on the left panel of this slide shows the 3 power curves constructed using the hub height wind measurements collected from WindCube Nacelle lidar, IEC compliant permanent mid tower, and the WindCube ground-based lidar at the same location, respectively. As you can see here, these 3 power curves are almost identical. We also applied a project-specific wind speed distribution to these 3 measured power curves to calculate the measured AEP values, which are then normalized to that of measured by using the IEC-compliant permanent mid tower. The results are tabulated in a table on the right panel of this slide. As you can see, the differences in AEP values are negligible, with slightly higher uncertainty using WindCube Nacelle-Mounted Lidar by about 0.1% here. AEP stands for the annual energy production. As I mentioned earlier, one of the study objectives is to evaluate the impact of different wind measurement locations on the power performance testing results. As the IEC standard -12-1 allows the wind measurements to be taken between 2 and 4 times rotor diameters upwind, with 2.5 times being the recommended location. We used concurrent hub height wind measurements from WindCube Nacelle lidar to construct power curves at different locations and applied the same project-specific wind speed distribution to estimate the measured AEP values. We then normalize the AEP values with that measured at 2.5 times rotor diameters as recommended by the IEC standard -12-1. The normalized measured annual energy production values as a function of upwind measurement distances are plotted here. As you can see, the measured AEP values decrease with an increase of the upwind measurement distances from the normalized wind turbine, from the nominated wind turbine. The maximum distance in the measured annual energy production between the 2 and 3 times rotor diameters is almost 3%, which could be significant depending on actual wind turbine performance. However, it should be noted that the uncertainty increases when the wind measurement location is more than 3 times rotor diameters away. To verify OEM's nacelle transfer function, first, we plotted the concurrent nacelle wind speeds using OEM's nacelle transfer function against those measured by the permanent mid tower and the WindCube Nacelle lidar, as shown here in 2 scatter plots on the right panel. As you can see, the correlations are excellent. The correlations are even better when we actually beam the concurrent wind speeds into 0.5 meters per second beams, As you can see in the plot on the left panel, they are almost on a one-one line for wind speeds less than 60 meters per second. Unfortunately, we do not have much data points for wind speeds above 60 meters per second. Nacelle-mounted lidar is a very unique and often the most reliable device to measure yaw misalignment. We plotted the yaw misalignment signals measured by WindCube Nacelle lidar and the OEM's yaw controller settings recorded in the scatter as a function of rotor RPM. As you can see here, the differences between the two are less than 2 degrees in average, with WindCube Nacelle measurements showing larger variance in the yaw misalignment, but overall, the results are quite satisfactory. Just to summarize, the power performance testing results using WindCube Nacelle lidar are comparable with those based on mid tower and ground-based lidar, but having the advantage to estimate the results based on the wind measurements at different upwind distances, which gives another dimensional information to understand the turbine performance. Nacelle-mounted lidar is a useful technology to support wind project operations and a unique tool to accurately measure yaw misalignment and verify nacelle transfer functions. This concludes my presentation, and thank you for your attention. And now I'm handing over to Elvira. Thanks.
Thank you. And thank you all for your presentations. It was quite interesting, and I think our audience liked it as well, as we have a lot of questions coming in. Let's dive into some of them. There is someone asking what will be the requirements in terms of verification procedures and intervals. I guess this is more for Luke.
Yeah, I can take that one. The requirements for the verification procedures, it could be talking about a lot of things. I don't know if we're just focusing on calibration or verification of the installation as well. But high-level response there, you do need to complete a full white box calibration prior to your campaign. As far as the interval, this was quite a contentious issue in the IEC, and I think where it's landed is that it's going to be up to the users to figure out what the right interval is. So you can potentially do multiple power curve tests with one calibration. You just have to justify it based on guidance from the manufacturer and what you're actually using it for in the use case. So hopefully answer that. It's a bit more flexible than some of the other methods we've seen, or at least for ground lidar requirements.
All right. Thank you, Luke. There is another question. I think this one will be for Hong. In slide 36, why is the database much lower for the WindCube Nacelle than for the permanent MatMast? If we go back to slide 36, yep. Oh, I think you went too far.
I think the database is almost, probably we didn't actually put them in concurrent period for comparison, but
I think it's 36 is the one with the table. It's a little, yeah.
Table? This one?
Yeah.
Oh, this one actually, yes, we didn't use concurrent data points for constructing the power curves for this study.
Yeah, or put another way, that last data set was filtered for LiDAR availability, which is going to have some data removal, whereas the first column does not have any of that data availability removal. Ooh, we might have lost Elvira. Trying to pick up the new question here. Maybe another one for you, Hong. Or actually, there was one for Alex. Sure. Alex, there was a question, is there a significant line of sight inaccuracy derived from nacelle movement and vibrations at longer ranges? How do you cope with that?
Yeah, I'll give a short answer on that one, but I think maybe the longer answer, if there's time for it now, is probably best to come from Leosphere. But generally, the Nacelle LiDAR devices and the wind field reconstruction algorithms are able to account for that vibration in the calculations that they make. So it's generally not a concern, given the work that the LiDAR OEMs have done towards those algorithms.
All right. Oh, she's back. Do you want to take it away, Elvira? Any questions? Oh. There's one for, can nacelle lidars be used in complex terrain? That's one we hear a lot. I might just try to chime in on that one. The IEC definitely excludes it. It's not allowed. There have been some projects, research type projects, and some commercial projects looking at this, but short answer is no. Longer answer is probably eventually, but we need more good data sets to try to run the validations to see how the wind field reconstruction handles the more complex flow and changes in height and terrain and all sorts of issues that develop with that. So we might be getting there. Hong, there's a few questions about the range, the ideal range, and what happens as you measure further out. You kind of did a plot on that, but what's the ideal range for the lidars to measure wind speed and direction? Do you want to respond to that one?
I mean, the wind lidar, WindCube, so Nacelle-Mounted Lidar actually can measure up to 700 meters, as Luke showed earlier, and but the IEC standard -12-1 allows the wind measurements to be taken between 2 rotors diameters and 4 rotors diameters. That's why we pick up the different distances between those between that range. But we did construct the power curves beyond that range, and we wanted to understand the blockage effect on that aspect, but we didn't present the results here.
Yeah, and similar from the D&V side, we've started to look at that, but we haven't. There's some great data sets out to I think it's almost 5 rotor diameters. If we look at all the data, even more than what's shown here. We can see what sort of impact we have. There's a question about other presentations going to be available. Is the webinar recorded? Just to make sure that's clear. Yes. It is being recorded. I think you'll get an email in a few days with a link to the presentation and the resources.
All right, thank you. And well, I'll try to ask another question. I hope my connection will be good. So there were actually a bunch of questions about the measurements in complex terrain. So if the lidars are as good in complex terrain, what are the procedures there? And well, if you can share a bit of your experience on this as well. I'm not sure if I'm still on, because nothing is happening. Sorry about that.
Sorry, was that for me?
I guess for all of you, but if you would like to go first, Luke.
Sorry, I was reading some questions. The question was on complex terrain.
Yes, that's right.
Is that? Yeah, we covered that a bit while you were disconnected, so I might pass it on to the next one. I don't know, Alex, do you have any comments? I think it'd be really good to hear from the OEMs, perhaps, on Nacelle lidar complex terrain. Where are we at?
From GE's perspective, we've only been evaluating in simple terrain at this point, so we haven't had any experience trying to understand the capabilities in complex terrain. So it's at this point not something that we've been working on.
From our side, Luke and Avila, so we have been using the Nacelle lidar, for the offshore wind power performance testing, and for quite some time. And for the onshore projects, initially we were trying to explore the use of Nacelle-Mounted Lidar for a complex terrain setting. But it seems that at this time, the new standard -50-3 doesn't allow that to be used for the complex terrain setting. And, we'd be happy if actually some OEMs or IEs could consider, or at least, to use that as for some kind of pilot projects, and that could, significantly reduce the power curve testing costs down the road.
Okay. Thank you, guys. And I guess we still have a few minutes. There is a question on the uncertainties, probably for Luke as well, this one. The audience is asking if the uncertainties were calculated based on 50-3 and 12-1.
Yeah, I can answer that. The short answer is yes, they were. We did have to assume what the classification uncertainties are going to be for the Nacelle lidar, and I think we used something in the range of 1 to 1.5% for the table that Hong shared. Eventually, that we think that's hopefully a little bit conservative and certainly representative, and hope it's going to depend on calibration site versus test site, as we discussed. So in some cases that might be high, maybe some cases that'll be low if you're getting to extreme conditions, but potentially that value goes to 0, and then the uncertainty on the far right there would be even lower than the mast and the ground lidar.
Okay. Yeah, I'm trying to follow up on other questions that are coming in. Measurement range instead of 2.5 of close proximity turbines. I guess the person to address this question, so I will feel comfortable about this one. So the question was, should the different measurement range instead of 2.5D be taken into account in case of close proximity turbines?
2.5, rotor diameters is recommended, by the IEC in the standard -12-1, and we haven't shown the results here. When the power curves actually, when the measurement distance approaching, further approaching to the turbine, like say less than 2 rotor diameters away, and depending on, again, I think it's depending on the rotor hub ratio, and that results actually presented here actually could change and you know, and again, you know, 2.5 rotor diameters is recommended by the IEC, and you know, but in most cases, you know, from our side, and I think we would like to use the measurement distance at around 3 rotor diameters away, less than 3. So we would maintain the low uncertainty from the wind flow aspect.
And there's a question about how many distances you can measure at once, and I think it's worth pointing out that the WindCube Nacelle can measure all these different distances in the same scan all at once. So we had data every 20 meters between something like 200 and 700 meters to you know, look at different differences. So I think there's a lot to do with that data, and we'll probably see some updates on that in the near future.
All right. Okay. Thank you very much, everyone. And we actually ran out of time, and I see that there are questions coming in, but unfortunately we don't have time to cover all of this today. Well, please let us know if you would like us to further contact you. And thank you very much to our speakers and to our audience. And yeah, here you can let us know if you would like us to contact you. And well, have a nice day and see you all next time. Thank you. Bye-bye.